Hi everybody, and welcome back to the video for lesson 7.1, which is all about solving differential equations. Now we have two learning targets today. The first learning target is to find a general solution to a differential equation, and the second learning target is to find a particular solution to a differential equation. But in order to do that, we're going to need to be given an initial value. Now let's talk about what exactly a differential equation is before we talk about how we would solve one. So, a differential equation is just the equation of the derivative of a function. A differential equation is just the equation of the derivative. When we are asked to solve a differential equation, so when the directions say solve, what we're really being asked to do is to find the original equation, f of x or y, depending on the notation. So in other words, we're just finding the antiderivative. So finding the original is the same thing as solving a differential equation when you're given the equation of the derivative. Now, the good news is we've been doing this already. We called it just finding the antiderivative. So let's review that right now. An example of a differential equation is right here. And the reason that this is a differential equation is, again, it's the equation of the derivative. When I say solve the differential equation, what I really mean is find the original equation. So we know how to do that. We know that we can just do the antiderivative. The antiderivative of dy over dx would just be y, and the antiderivative of 3x squared would be x cubed, and then we need to write plus c. Now, this plus c right here is what makes this the general solution to a differential equation. And the reason that this is called the general solution is because we don't know the value of c. We know that our answer is going to look something like this. It's going to be x cubed plus something in general, but we don't know the specific value of c that might have been there for this equation because we can't tell. When we take the derivative of that number, it goes away. So it might have been there, but we don't know what it is. Another name for this type of solution, so another name is what's called an indefinite integral. When your answer has a plus c, it's called indefinite integration because we can't actually find the value of c, at least not yet. The big new idea of today is that in addition to finding a general solution, which is when our answer has a plus c in it, so a general solution is when our answer has a plus c in it. In addition to finding that, we're actually going to be learning how to find a particular solution to a differential equation. In a particular solution, we can actually find the correct value of c that would have been in the original equation. We just need a little more given information in order to make that happen. That additional piece of given information is what's called an initial value. Now, an initial value is just one xy combination, one ordered pair that we know for sure was part of the original equation. We can use this information to actually calculate the c value, which we call finding the particular solution. Particular, there we go, solution. So you'll notice that this example down here looks very similar to the example that we just did. It's just got a little additional information. For example, we still have the same derivative equation. We're just given an additional piece of information that f of 2 is equal to 14. Let's look at how we can use that to actually find the particular solution. So the first step is find the antiderivative. The antiderivative of dy over dx would be y. The antiderivative of x cubed is 3x squared. Of 3x squared is x cubed. There we go. I said that backwards and then I wrote it backwards, is x cubed. And we know that we have this plus c. Now, in order to actually figure out what the c value should have been, we're going to go ahead and take this initial value and plug it in. In this initial value, the x is 2 and the y is 14. So if I substitute those numbers, I have 14 equals, instead of the x, I'm going to have 2 cubed plus c. Now, if I cube the number 2, I get 8 plus c, and if I solve for c, I can subtract and I get 6. I like to think about these steps as almost like taking a detour to take a second to find c before we go back and actually write our final answer. Because we know now that c should be 6, our final answer is going to include that information. So our final answer here would be y equals x cubed, and then instead of c, because we found that the c should be 6, we're going to put plus 6. This right here is the particular solution because now c is a known value. So we actually know the value of c that satisfies this differential equation because we had that additional piece of information, the initial value. Let's go ahead and practice this. So for the first few examples here, the directions say, find the general solution. As soon as I see that the directions say, find the general solution, I know that my answers should have a plus c in them because I'm not going to have enough information to actually find that c value. So in order to do this, I can just go ahead and do the antiderivative. The antiderivative of dg over dt would be g of t. The antiderivative of secant squared is tangent of t. The antiderivative of 2t is t squared, and the antiderivative of 5 is 5t. And then at the end, I'm going to write my plus c. In the next example, if I know dy over dt is e to the negative t power, I know my original equation would be y, or y of t equals. Now in this example, I would have had to use chain rule. So actually, let me erase this and scoot it down because I need a little bit of extra space here. So y equals. In this example, I know that when I took this derivative, I would have been using chain rule because of that negative. So to undo chain rule, what we learned is that we have to divide by the derivative of the inside, which is the chain, which in this case is -1. Now nothing cancels here, and so I just do the antiderivative now of the outside. The antiderivative of e is just e to the something, and because of that dividing by -1, I just put a negative at the beginning. Don't forget that at the end, you should have your plus c, because that is what makes this the general solution to the differential equation. So this is, again, the answer, and this is, again, the answer to this question. This is going to be a lot of review of what we did in Unit 6, where we're just doing antiderivatives. We're just giving it a different name now, and we're sometimes going to actually be able to find that c value. We'll do a few examples like that in a second. For problem number 3, again, I'm going to do the antiderivative. So I'm going to have y equals. Now, when I see that this problem has a divided by x here, a lot of times I like to rewrite that as a -1 power. Whenever I see this -1 power, I know that the antiderivative would have had to be natural log of the absolute value of whatever is inside there. In this case, that would be x. So my antiderivative here would be negative than the natural log of the absolute value of x. And at the end, I'm going to go ahead and I'm going to put a plus c in order to make sure that this is the general solution. I know I can stop there. I don't need to actually find the c value. Last but not least, what if I see a problem like this one? Again, this is a problem where I can identify right away that the chain rule would have happened. And I know that because the tangent is inside of the square root function. So I oftentimes rewrite this as, I'm going to get a little bit more space here. I oftentimes rewrite this as the tangent of x to the 1/2 power times secant squared. Sometimes that just makes it a little bit easier to see that the inside function here is tangent. Now, step 1 would be to divide by the derivative of the inside, which in this case is secant squared of x. Now that means this secant squared and this secant squared are going to cancel. So all I really need to do now is take the antiderivative of the outside. The antiderivative of a 1/2 power I would add 1, so I get 3/2 power, and then multiply by the reciprocal or divide by 3/2. Either way, you get 2/3. I'm going to go ahead and leave the inside alone and then put my plus c at the end. So far, we've now practiced finding the general solution to a differential equation. Let's do an example where we can actually find the particular solution. So in these directions, it says find the particular solution. And you'll notice that in the problem, we're actually given an initial value here as well. That means that your final answer should not have a plus c in it. You should actually find the value of c that satisfies this differential equation. So step number 1 is going to be to do the antiderivative. The antiderivative of dy over dx would just be y. The antiderivative of cosine would be sine of x. And I'm going to put my plus c there for now as a temporary placeholder. Now we're going to sort of take a minute and figure out what that c should be. I like to think about this as taking a detour. So a lot of times in my work, I'll draw a scribbly line just to be like, hey, I'm taking a detour for a second before I write my final answer. In order to figure out the value of c, I'm going to take this initial value and I'm going to plug it in. Again, the x is inside the parentheses and the y is on the outside of the parentheses. So I'm going to have 7 equals the sine of, I'm going to plug in the pi over 2 plus c. Now the sine of pi over 2 is 1. So I have 7 equals 1 plus c. And if I subtract, I get that c is 6. Now my detour is over. I actually found my c value. So I'm going to go ahead and just plug that into my equation. Again, I'm taking the c and I'm replacing it with the number 6 because now I've determined that the value of c should be 6. So my final answer will be y equals the sine of x plus 6. Because now I know that the value of c should be 6. All right, let's take a look at number 6 here. Now, number 6 is, again, a problem where I'm given an initial value. So that allows me to be able to actually find the value of c at the end here. Step number 1 is going to be to do the antiderivative. So the antiderivative of dy over dx is just y. Oops, I'm still on the highlighter. The antiderivative of dy over dx is just y equals, now I have e to the negative x. Now, when I see this negative x here, just like I saw in the problem I did up here at the top, when I see that negative x, I know that the chain rule would have happened because it's not just an x, it's a negative x. So step 1 is to divide by the derivative of the inside, which is negative 1. Now, nothing cancels here, so I'm just going to do the antiderivative. The antiderivative of the outside, the antiderivative of e to the something is just e to the something, but I'm going to multiply by negative 1 because of that dividing by negative 1. I'm going to put a negative there. Now, the antiderivative of 2 is just 2x, and I'm going to temporarily put a plus c until I determine the value of c that is correct for this problem. Now, in order to find the value of c that is correct for this problem, I'm going to go ahead and plug in my initial value. So my initial value here is the x is 0 and the y is negative 4, and I'm going to plug that in. So I'm going to have negative 4 equals negative e to the negative, again, I'm plugging in a 0, and then plus 2 times, again, I'm plugging in a 0, plus c. Now, e to the 0 is just 1. So I'm going to have negative 4 equals negative 1. 2 times 0 is 0 plus c, which means I figure out that my c value is negative 3. Now, again, I know what c is. So in my final answer, I'm going to replace the c with the value that I've determined is correct for this problem. So my final answer is going to be y equals negative 1 e to the negative x plus 2x minus 3. And I'm filling in that negative 3 because that is the value that I've determined is the correct value for C based on the initial value that I was given in this problem. All right, that is it for today's video. Thank you guys so much for watching, and I'll see you soon for some practice.